Hi, in this video, we'll be going through the mixed strategy Nash equilibrium and how we're going to find this mixed strategy. So why is there a need for mixed strategy? In the previous videos, what we learned is a pure strategy where you only have one action per time. But this might fail in certain cases, such as the matching pennies case. So you see, if a player has a penny and must choose whether it displays heads or tails, if the two pennies match, then player 2 wins. If they don't match, then player 1 wins. In this scenario, you draw the bi matrix, and actually you can notice that there is no Nash equilibrium. And to fix this problem and find an equilibrium, we need to have the notion of the mixed strategy. And a mixed strategy is basically a probability distribution where you play a probability of P for heads and a probability of Q for tails, but P and Q must add up to 1. And this can happen for K players or N players, where each player has K actions. And with this example of the matching pennies, we look back again. With now the mixed strategy idea, all we need to do is specify playing heads with probability P and tails with probability 1 minus P. And if our P is 1/3 and 1 minus P will be 2/3, then this can be a mixed strategy, but it might not be the most optimal one. And we can then see how we're going to find it later. So some things to note is that if the mixed strategy is like probability 1 to be heads and 0 to be tails, then it can be viewed as the pure strategy. So a pure strategy is in turn like a mixed strategy, while with probability 1 and 0. So if you remember the definition of the Nash equilibrium, it is the best response to each other's pure strategy. And so we can extend this definition to mixed strategy, and it is just basically saying your mixed strategy is the best response to the opponent's mixed strategy. If we look back at the example, let us first see this where player 1 plays half-half and player 2 plays 1/3, 2/3. Then we can calculate the payoff for player 1, which is, you just think, so this is the probability play half, this is the probability 1/3. So the probability heads come out is this. Then this is like the probability. Then we just need to add all the payoff together. So this is the probability with -1. So it's like this is the portion that it will come out with -1, probability 1, probability -1, probability 1. And when you add them up, you get 0. And similarly for the payoff for player 2, it is just taking the probability multiplied by what is the payoff per each box. And you see that the payoff is 0. So in either cases, the payoff is 0. We will now illustrate the notion of the Nash equilibrium by considering the case of two players, which is what we have seen. And so, if player 1 believes that player 2 will play the strategies with this probability, then player 1 expected payoff will be the weighted sum. So this is your probability of occurring, and this is your payoff of that event, which is basically over here what we are saying. You got this and you multiply -1 plus this multiply 1 plus this multiply 1 plus this multiply -1. Because you have a chance of playing either of the strategies. So any of these outcomes can come about. So you need to take account all the different payoff to your final payoff. So it's basically the sum of the payoffs. And now to find a mixed strategy Nash equilibrium is having a profile such that all other strategies is less than this mixed strategy Nash equilibrium, so that you don't have the probability to deviate. In that case, now we can equivalently say that it is just okay. So remember we have the summation over here, so we can actually write the summation in this form, and it is actually this part don't determine on K, so we can take it out, so you only left with this. This is the pure strategy best response to PJ star. So it is actually the sum of certain pure strategies added together. And the mixed strategy will only be a best response if it is put together by a series of probabilities of pure strategy. So a mixed strategy must be made out of pure strategy best responses, if there's any. So for example, let S1 equals to this, and if S11 is a unique pure strategy, then it's also going to be the unique mixed strategy. If S1 and S12 are both pure strategies, best responses, but S13 is not, then the mixed strategy has to be of the form Q, 1 minus Q and 0. S13 will not be used in the mixed strategy at all. And if all three are pure strategy best response, then you have to use all three strategies in your mixed strategy. So that's the idea behind this. And so let us now take the example of matching pennies to determine the Nash equilibrium for mixed strategy. So what you do is you let player 1 have the probability of R choosing heads and 1 minus R choosing tails. For player 2, you have Q and 1 minus Q. Then the payoff for when you have chosen heads, so in this case, this scenario, it is minus 1 times Q plus 1 minus Q times 1. And the payoff for choosing tails is minus 1 plus 2Q. So you only choose heads if this is greater than this payoff. And for this to be greater than this payoff, Q has to be less than half. Hence, the response function is your response is you get you have 1 if 0 is Q to half. And then your probability of choosing a heads is 0 if Q is larger than half and between 1. But if Q is half, then your probability of choosing heads can be anything. And then now we find the best response to R for Q's probability. And it's the same thing, you find the payoff function and we choose heads. So we choose heads if it's larger than, which means R has to be larger than half. And we again similarly write the best response function. And if we draw the best response function, R is this line. Remember? So R is 1, 0, 1, then everything, then 0. So it's 1, then you get, at half you got all the numbers, and then 0. Similarly for Q, it is first 0, then everything, then 1. And the Nash equilibrium is always the intersection of best response functions. And so the best response function is when they intersect, which only happens at half. So in this case, Q is half and R is half. So the strategy to play is half-half half-half. That means that both players can be randomly choosing tails and heads with equal probability as the best strategy. And the Nash equilibrium theorem, the Nash theorem, says that every finite normal form game has at least one Nash equilibrium, possibly involving mixed strategy. And the proof follows from the fixed point theorem, which we will not go into. So now we have another claim, is that if the pure strategy is eliminated by IESDS, then it won't be played with the mixed strategy, which is what we already said, and that is really the understanding that the mixed strategy is made out of if and only if there's pure strategies in this mixed strategy. So if there's only 2 player strategies left for each player, then we can then approach with the discussion earlier. So we use the IESDS to eliminate the pure strategies so that we know those won't be in the mixed strategy as well. So an example is over here. We use the IESDS to eliminate the dominator strategy M and C. So you delete M, you delete C, you're left with this by matrix. With this argument now, we can use the same argument when we use R and 1 minus R, Q and 1 minus Q to get the best response function. So once we get the best response function, we are able to draw them out and see where the intersection lies, which is here. In this case now, Q is half and R is 1/4. So they also intersect at 0, 0 and 1, 1. So in the original game, you have, this is going to refer to T and L. So 1, 1 is you play T with probability 1 and L with probability 1, and the other case is you play zero, 0 is when you play B with probability 1 and R with probability 1. So these are the pure strategy, and the mixed strategy will then be this 1/4, 0, 3/4 and half, 0, half. So the reason why you have the 0 in the middle is because you cancel out the M and C. That means you'll never play them, which means the probability of playing them is 0. So I hope now you understand more about the mixed strategies in game theory and what is a mixed strategy Nash equilibrium. If you have any questions, leave it down in the comments, and feel free to like this video, hit the subscribe button, and I'll catch you again. Bye!